In today's lecture, we're going to continue our look at techniques of integration. And in the last couple of lectures, we've been working our way through different techniques and different methods. In the last lecture, we started... And I don't want to use this, all right. Now, in the last lecture, we started partial fractions. All right, and we met a fairly interesting guy, or I find him interesting, by the name of Oliver Heaviside. Now, just to recap, because some of you might not have been here yesterday, or you may have forgotten, we're going to look at the integrals of rational functions. So function in this form where both f and g are polynomials. Okay, so if you look at these examples here, this is a rational function, this is a rational function, and these two are not. Okay, now, shush! Everything okay? All right. For the purpose of our investigation, we're going to concentrate on integrals of functions like this, where the highest degree or power up top is less than the highest degree down the bottom. Okay? If not, then we can use long division to put it in a suitable form. All right, so I motivated the study by posing this integral here, and it's a hard integral to work out, but we can break it down to two known integrals, or integrals that we can actually evaluate. And essentially, all it was about was, in this case, playing with the numerator. Okay, you can see if I add x and take it x away, I can then break it up and form a combination of two functions that we can integrate. Okay, so that's a general idea with this method of partial fractions. Now here's a whole big mess of stuff that I don't expect you to really understand. My whole point of the lecture yesterday was to show you rather than actually tell you all the gory details. We also looked at a basic method called the Heaviside method. Now the Heaviside method is a nice method because it's fast, and there's basically zero algebra involved with the Heaviside method. Okay, so essentially you just end up covering up parts of your integrand and making substitutions. So here's Heaviside. I did talk about him a little bit yesterday. Essentially, he claimed that mathematics is an experimental science and definitions do not come first but later on. What he's trying to say there is, play around, experiment, try things first, and then formalise things later. And I would agree with that in maths. That's what a lot of mathematics is. Okay, so just to go through the solution to the first example that I solved, you can see we factorised the denominator into distinct linear factors. All right, then I broke it up into this combination for big A and big B, certain constants that we want to calculate, right? If we can calculate those constants, then I can do the integrals, right? I can do the integrals. So that's the whole point. Okay, so the Heaviside method involves looking at the integrand, covering up one of these, and making a suitable substitution. So if we look over here, to find A lies above x plus 3. So let's go to our integrand, cover up the bracket containing x plus 3, and substitute in x equals minus 3 to give me A. All right? So essentially that's what I did in the next line. I covered up that, substitute in x equals minus 3, and then that gives me my constant A. So to calculate b, I see b lies above x plus 2. Go back here, cover up the bracket containing x plus 2, and substitute in x equals minus 2. That'll give you b equals minus 5. So, if I realise then that I've got my two constants, I can write my integral in this fashion and then integrate to obtain logarithms. Now you can simplify this if you want to. I'm just going to leave it as is. But that was the basic method that we learnt yesterday. Okay, it's a powerful method. It requires hardly any algebra.
Chris,
yes?
Test, if we don't simplify it, do we get points?
Oh, that's a good question. The question is, in a class test, should I simplify it? I guess the answer is yes. But, in my opinion, that would be okay. That would be okay, because it's not about whether you can simplify logarithms. It's about whether you can do the integration, right? Okay? But some tutors may absolutely disagree with what I've just said. Okay? You come to me if they give you a hard time. All right? All right. So just to step through the process. Once more. Okay, the Heaviside cover-up method. It's great. So to get our letter A lies above x minus 1. So you cover up x minus 1 and you substitute in x equals positive 1. All right, so A is going to be what's remaining here with x equals positive 1. All right, simple. So for B lies above x plus 1. Go here, cover up x plus 1 and substitute in x equals minus 1. Okay, so if I cover that up and substitute in x equals minus 1, you're going to get something like this. All right, and finally, for C lies above x minus 2. So I cover that up and plug in x equals positive 2. So I'm going to get something like this. Okay, pretty easy. So now I just take those values and do my integration. Thank you. All right, so we know just from the structure, in the top right-hand corner, we're going to get logs in our answer. Okay? So logs are going to come up in our answer. So let's actually put in our A, Bs and Cs and do. Okay, so I'm going to get 3 logarithms. All right. Okay, so any questions? Any questions so far? Now, there are steps or problems where the Heaviside method won't be so useful. Okay, the Heaviside method's a great method, but you can't use it all the time. So this is the example that we kind of left our lecture on last time. And essentially this can be broken up, right? I'm always trying to teach common sense first when you try to solve problems. There'll be people that try to do this by, partial fractions and, go through and do the general method. And it just, it's just not necessary. Okay, so observe the following. Oh, equals. Now, if I split up the, thank you, the numerator, I can break it up into chunks that I can integrate. So if I break up that first part, I'm going to get 1 on x plus 2 all squared. And the second part is just going to be 1 on x plus 2 all cubed. Now I can integrate both of those terms almost immediately. Okay, so this question or this example is really designed to actually show you the setup for, I guess, the decomposition of this repeated linear factor. So when we have this cube down the bottom, we say this has a repeated linear factor because x plus 2 is repeated 3 times. Well, I guess it's repeated twice, right? So in general, this would be the setup that you would be chasing. Where big A, big B, and big C are constants that you need to calculate. Now, we've already calculated them just in that top line. Okay? Big A is going to be 0, big B is going to be 1, big C is going to be 1. Okay, so all I need to do is integrate those two and I'm done. It's a squared. Okay, so common sense really ruled the solution to that exercise. Break up the numerator when you can. Don't try to use fancy techniques when they're not, they're just not suitable. Okay, so how did I know how to break that up? Well, I look in a denominator and I can see it x plus 2. So all I have to do is break that up into x plus 2 plus or minus something else. Okay. So in general, when you have a repeated factor, look at the bottom of each term and you see that the power increases. So here's another example. We're asked to evaluate the following integral. What's the decomposition? Well, you've got some repeated linear factors, the x plus 1s, and the x on the bottom. So it would be something a little like this. So can we find big A, big B, big C, and big D? Now that looks like a lot of work, but it's not. Can anyone suggest something? Say again? Yes. If you look on the top of your integrand, the numerator, you've just got a 1 sitting up here, right? If you add x and take x away, and break it up, you're going to get some cancellation straight away. If you continue doing that throughout this problem, you can get A, B, C, and D, reasonably quickly. So I can break that up into 2 bits and get some cancellation right away. What was that? All right, so when you break that up, you're going to cancel off the x's and the x plus 1s. And you're going to get something like this. Can anyone suggest anything now? Well, any suggestions? Am I missing something in there? What am I missing? Oh, yeah. That would have been too easy. So I can integrate that second term straight out. What about the first term? Do the same thing, yeah. So add 1 and take 1 away up top. Okay, so continuing in this fashion, you'll get down to the following. Hey, how you doing? All right, so you'll actually get down to the following. Okay, so you can continuing in that fashion, you'll get the following. So each of those bits can be integrated. You're going to get logs in the first 2 terms and the following in the second 2 terms. Okay, so this is going to go to plus 1 on x plus 1, and this is going to go to this over 1 on 2 bracket x plus 1 all squared, plus a constant. Okay, now the 2, yes? So this is in here. So this is minus. Hang on, no, it should be plus, right? Yep, is that what you're saying? Thank you. All right. Now, the 2 examples that I've given you, they're kind of just designed to show you, just common sense is the first tool that you should use, right? Don't use methods if you don't need to, right? Just use the simplest method. But of course, this won't work all the time. You'll try to break the numerator up and it just won't give you what you want. Okay, so let me teach you a general method for these partial fractions. Okay, so here's a good example from a class test. How can we integrate this problem? Well, let's have a look at the denominator. You've got a linear factor here, x minus 2, and then a repeated linear factor. So, we're going to have to break that up in some way. Any suggestions? How would you break that up? Anyone? Hands. Yes.
Try and make it like the top one that's like something like x minus 2.
You could try to do that. You could try to play with the numerator and try to make it like x minus 2. Difficult. I can't see it. Okay? So what I'm going to do now is actually show you a very general way of doing this. Okay? So the decomposition that I'm chasing would be something like this. Yes. Okay? So that's what I'm chasing. Essentially, what I'm going to show you now is that it's not exactly the Heaviside method. It does involve a little bit of algebra. But essentially, it's just looking at the integrands and comparing them. So, what I'm going to do is just compare the integrands and multiply both sides by what's down here. Okay, so if I do that, I'll get some cancellation. And I'll get an important equation that I'm going to work with. Okay, so if you've seen this method before, which some of you may have, you've got a couple of choices here. You can expand the brackets if you want to and equate the coefficients. So all the x squareds on one side have got to equal all the x squareds on the other side. All the x's on one side has to equal all the x's on the other side, etc. I'm not going to do that. Okay? Essentially, I'm just going to choose values of x and find a, b, and c, hopefully, in a quick and easy manner. Okay, so if I substitute in, say, x equals minus 3 into that bottom line, then I'm going to get a lot of cancellation, right? So I can find c straight away just by plugging in x equals minus 3. So we're going to substitute x equals minus 3 to obtain the following. Well, that's going to be 0, that's going to be 0, this is going to be non-zero, and we can work out the following. So c equals 3 if you just solve that. Okay, can anyone think of another good value to sub in for x? 2, yes. 2. All right, so if we sub in x equals 2, we're going to get, that's going to disappear, that's going to disappear, and we're going to be left with something involving a. Okay, so if you solve this, we'll get a equals 1. Okay, so we've got 2 of our 3 constants. We're feeling pretty good. What's that? Yeah, you could equate x squared, yeah. I guess you could substitute in x equals 0. 0 is a pretty easy number to work with. Just sub in x equals 0, right? All right, so on the left-hand side, I'm going to get 9. On the right-hand side, I'm going to get something like this. Now, I already know what A and C are. So this is going to give me B equals minus 1. So I've got my 3 constants that I'm chasing. So now I can integrate, hopefully. Oh, minus 1. Sorry, I left the minus off. Thank you. Okay, so let's integrate. So call this I. So now I'm just going to integrate. I'm going to get a couple of logs and just 1 minute. Or what? No, actually, I hear you now. What's up? Just because I have the power to make that choice, and so do you. You have the power. Okay. Just 0's an easy number to work with usually. Okay. You want to. I mean, you could sub in x equals pi, or root 2 or something, you know. But it's not going to be nice. Too nice for the calculations. Okay. So it's up to you to choose it. Okay. So we make this integration. And we're going to get something like that. All right, any other questions? Any other questions? Okay, so that is a good indication of a question that you may get on a class test. Okay, a little bit of work. That would probably be worth, I don't know, 3 marks. All right, so we've been looking at a lot of method here. This is actually a little bit further on in your notes. Where do we use these kind of techniques? Okay, well, an important problem is the study of population dynamics. And we'll see a bit later on in the semester an equation like this called a differential equation. Now, what mathematics does a lot of the time, or tries to do, or aims to do, is to predict real-world phenomena. Okay, it tries to predict it. If you can mathematicize it, model something, you can make a prediction about this. Now, if P is a population of some species at time t, then you can show, or it can be shown, the function and its derivative are related by this equation 3 called a partial differential equation. M is just a constant. What we would like to do is, like any other equation, is to solve it. So the unknown here is not a number, it's a function. Okay? All right. Okay, all right. Now, solving differential equations is just in many cases uses integration. So what we can do with this differential equation is to rearrange it and integrate on both sides with respect to t. So you get a bit of a cancellation there. So essentially what you want to do is integrate this left-hand side somehow. Remember, m's a constant. This is perfect for using the partial fractions approach. Okay? So how do you do it? Well, you can split up the integral into 2 subintegrals and then integrate. If you consider 2 separate cases, then the solution looks a little bit like this. So think of this as time and this as population. You can see if I have a low starting population, the population increases and then heads towards this number m, this limit m. Okay? If I have a higher population to start off, things don't increase quite as fast. If I have a very high population, things decrease. So either way, you end up having a population that approaches some limit called the carrying capacity. Okay, this is the sort of optimal amount of people or numbers that the environment can support. Okay. Anyway, we'll have a look at this a little bit later in the semester, but to solve this, one way of solving this problem is through partial fractions. Okay, so there are cases where you try to integrate functions and the denominator won't factor, not over the reals anyway. So what do we do? What do we do? Well, again, we play with the integrand so that the numerator is the derivative of the denominator. How does that help us? Well, you can integrate and get something involving a logarithm. So how does it work? Well, let's have a look. Let's have a look. All right, so if you try to factor the denominator, you can't, at least over the reals. So what we are going to do is try to make the numerator into the derivative of what's on the bottom. Okay, so if I look at the bottom, what's the derivative of x squared plus 4x plus 5? 2x plus 4. Do I have it on the top? No. But what? What?
You plus a 4.
Yeah, what I can do is make that numerator into the following. And so I'm going to bracket it and break it up into two parts. Okay, so now with the second term, can anyone suggest something to, some sort of method, or complete the square? Yes. So completing the square is going to be important for this second term. So to complete the square, you just look at the coefficient of x. That's what it's all about. You halve it, you square it, and you add it and take it away. Okay, so let me just, this is a positive 4. You halve it, square it, add it, and take it away. Let me show you what I mean. So that's exactly what I've done. I've got a perfect square in the first 3 terms. Now you could argue, well, I can just break the 5 up and, get 4 plus 1. Yeah, sure, you could do that. Okay, so now we can integrate both of those terms. The first term is going to have an integral involving a logarithm. The second term is going to have an integral involving inverse tan. Okay? So the integral is going to be something like this. So the logarithm minus 3 times tan inverse x plus 2, plus a constant. Okay, so there was really 2 steps there. we manipulated the the numerator, and then we broke it up into two separate parts. Okay. Now, there are other ways of doing these questions, but I'm not really going to concentrate on this. You can use an inverse hyperbolic tan, but I'm not going to concentrate on that. So let's look at an example from a class test. All right, you're given an integral, and you're also given the integral of something involving 1 on u squared plus a squared, where a squared is a constant. Calculate the integral. All right, so firstly realise that the denominator doesn't factor. So what I'm going to try to do is play with the numerator so I get the derivative of x squared plus 2x plus 10. So I need to turn that that x into something like 2x plus 2. How can I do that? Well, what I can do is actually multiply by 2, divide by 2, and add and subtract. Okay, so I'm going to I guess that should be a 4, right? Okay, so now what I can do is bracket that up, break it up, and see. Oh, hang on, that's not right. Oh, no, it is right. Oh, second guessing myself.
Shouldn't it be 2?
Yeah, there's a half out here. Yeah. Okay, you with me? All right, so I can break this up. No, you're right, it should be 2. Nick, what am I doing? What am I doing? What are you paying your hex for? Come on. Demand a full refund immediately. All right, we happy with that? Okay, so let's break that up. Now, the minus 2 and the half will cancel out, so I'm going to be left with 1 on the top. What can I complete the square down to here? What are we going to get on here? It's going to be x plus 1 all squared plus 9, 3 squared, right? Okay, so let's integrate these two things. So if I call that I, so the integral of this will be a half log of what's on the bottom. And the integral of this, we can use our little formula here. Hey. I finally got there. It was a bit painful, but I got there. Okay. Any questions? Yes?
We need the absolute value sign because x squared plus 2x plus 10 greater than or equal to 1.
No, I think the absolute value signs are okay. You can't keep them and be wrong. Okay? Yeah. Good. That's a good question. All right. So now I'm going to show you some combinations of the rules. These are just ones that might pop up where you just have to, of course, make a decision on how to solve them. What do I do? What do I do? Okay, decision we need to make is, can I factor x squared plus 2x plus 3? Can I? No, I can't. So, the breakup is going to be something like this. The decomposition now notice up top, I've got bx plus c, and I've got a quadratic down the bottom that won't factor. This is standard procedure for these problems. Okay. So I'm going to have to do two integrals. The first one's easy enough, but before I get there, I have to calculate a, b, and c. All right, so I'm not going to use Heaviside or anything like that. I'm just going to go to the general method where you look at the integrands and multiply both sides by everything down here. So I'm going to get some cancellations. Okay, so you can, if you want to equate the coefficients, or you can just substitute in, whichever method is you're more comfortable with. Okay, it's up to you. All right, so all right, well, I just subbed in x equals 0, x equals minus 1. And that led to the following. Now, I'll leave you guys to fill in the details for A, B, and C, or the working if you want to. So let's have a look at the integral now, under that decomposition. Okay, so the first integral is easy. The second integral, well, it's like the example that we just did. You're going to have to play with the integrand, 2x minus 3, and break it up. So that's going to lead to the integral is going to lead to a logarithm and an inverse tan. Okay, so I can integrate the first one okay. Okay, so if I break that up and complete the square down here, I'm going to get something like the following. Okay, complete the square down here. I'm going to get x plus 1 all squared plus 2. Okay, so all I need to do now is do the final integral. Oh, sorry, yes. I've got logs on the brain. Thank you. inverse tan. All right, so these are, they're not trivial questions. And this one pretty much uses everything that you've just learnt, right? All right. What would be the setup for this one? You see, we've got some repeated linear factors and something that doesn't factor, the x squared plus 1. Okay, so this would be our decomposition. Hush, hush, hush. Okay? So we've got to get 4 constants, A, B, C, and D. Okay, well, I'm going to leave this as an exercise. So let me just write down what the integral actually is. Okay, so have a go at it. Have a go at it.